Hello again. This is my hopefully final attempt at recording nodal analysis. So we are looking at the nodal analysis for circuit analysis, and in nodal analysis, the most important aspect of nodal analysis is to try to find the number of nodes in a circuit and to label each of those nodes, associate each of those nodes with a nodal voltage, and then try to express all the currents that are at the different nodes as functions of those nodal voltages, and then set up a set of systematic linear equations to solve for the unknown nodal voltages, and finally to find the number of all the unknown currents in a circuit by using those nodal voltages. So that's what we will be doing today, and I'm going to illustrate that with an example looking at this particular circuit that's on the board. So let's do nodal analysis on this circuit, and what we will need to do nodal analysis is to recollect KCL, Kirchhoff's current law, and what happens with that at the particular node. Also recall Ohm's law, which basically says that the current through a particular resistor or device is a function of the voltage across that particular device and the resistance value of that device. So the equation for Ohm's law is V is equal to IR. We will use that, and also Kirchhoff's current law, which essentially says that the sum of all the currents at a node should be equal to 0. In other words, the net flow of inflow of current into a node must equal to the net outflow from that node. And when you add both inflow and outflow, they should cancel each other out. And nodes should not have any storage attached with them. So all these definitions we have already seen, and so now let's go use those to do nodal analysis on a particular example circuit, which is shown on the board. Okay, so here are the steps that you'll have to follow to do nodal analysis. So the first step is to identify the number of nodes. So step 1. So these are the steps we'll do, okay? And we will do these with this particular example. So, all right, so first of all, I'm going to use different colors to indicate the different nodes. So let's look at the circuit, inspect it, and see if we can find any obvious nodes that exist. So a node, as we looked at earlier, a node is defined as a point where two or more circuit elements are connected to each other. It does not matter what type of circuit element, passive or active, independent or dependent, it doesn't matter. As long as you have two circuit elements connected together, that becomes a node. So the first node would be this one, in which you have the 20 volt voltage source and the resistor, 5 ohm resistor are connected. So I'm going to circle that. So this is node number 1. And I'm going to give it a name. I'm going to call it A. This is node number 2. You have these 3 resistors, 5 ohm, 10 ohm, and the 10 ohm all connect together. So this becomes my second node. I'm going to call it B. And here is my third node again. You have 10 ohms, 20 ohms, and the 4 amp current source all connect together. So this becomes my third node. I'm going to give it a name C. Okay, so now I've named all the nodes. I have to associate a voltage with each of those nodes. So therefore, I'm going to give the name for the voltage at this point, which is point A. I'm going to call it V sub A, or voltage at the point A. I'm going to call this VB, which is voltage at the point B. I'm going to call this VC, which is the voltage at the node C. Okay, then next is we have one big glaring node that we haven't looked at, which is the bottom line. So this line, you see you have the 20 volt current voltage source, you have the 4 amp current source, the 20 ohm resistor, and the 10 ohm resistor, all are connected, joined at that point. So this is a fairly large node, and it's a single node. So I'm going to call this the reference node, and the reference node in circuit analysis gets a special name, and we call that ground. And so therefore we're going to call this ground, and I'm going to put this symbol right there. This becomes the reference node, or in other words, all the other voltages are expressed with respect to this node or the ground node or the reference node. Okay? So every circuit, whenever we do circuit analysis, one of the few things that we always must do is to identify the reference node, call it ground, and then express all the other voltages in that particular circuit with respect to that reference node. Okay? Alright, so therefore we have identified all the nodes we need, we have given it a name, we have associated a voltage at each of those nodes. Okay, next is we are going to go through these nodes and we're going to write KCL. Now we typically don't have to write KCL at the ground or the reference node, it is usually at the other nodes that we will write. Okay, and in fact, ground node is considered zero voltage or reference. So zero, we already know the nodal voltage, which is zero, so we don't have to calculate for that. Now, let us also at the same time look at the circuit a little bit carefully and see if we can identify any obvious voltage values that will make our analysis a little easy. Okay, so by inspection, we see that at node A, we have a voltage source that is connected between ground and that node A. So the voltage at that point A is 20 volts above ground, and 20 volt because this is a 20 volt voltage source, independent voltage source. So therefore, this point BA, so by inspection, we can write B sub A is equal to 20 volts. This is an important result. So we put a box around it. Okay? That's an important result. Okay. Next is we need to now write KCL at node B and node C. So at node B. Okay, if I want to write KCL, and KCL basically means we need to look at what are the currents that are flowing in, what are the currents that are flowing out. So let's first draw the current directions at the node B. So before we do the current directions, we have to make an assumption in order to proceed. So we don't know whether the current is flowing from node A to node B or node B to node A. So in order to make our life easier and to proceed with the analysis, we are going to make a standard assumption. So this standard assumption is that we will always assume that we will assume that it's a standard assumption we make for all analysis, that B sub A will be greater than B sub B will be greater than B sub C. So this is a standard assumption that we make. Now, it does not matter if this assumption is incorrect, because as we know, if we make an incorrect assumption, we will get a negative value. If you make the right assumption, we'll get a positive value. So therefore, it doesn't matter if this assumption is wrong. We can proceed, and then if our assumption were to be wrong, we will get negative value. And therefore, we know which is the right way which is the right polarity for the voltages that we have solved for. Okay? So therefore, let's proceed. So we make this assumption, and therefore it helps us to establish the direction of currents. So using this assumption, if I go back and look at node B, and I'm looking at what will be the direction of current, we can easily figure out that since the node voltage BA is higher than VB and current flows from the higher potential to the lower potential, we can very clearly see that the current direction should be along that way. And I'm going to give that current a name, IAB, I sub AB, which means it's flowing from A to B. Similarly, if I look at this node and this is ground, so obviously VB is at a higher voltage compared to ground, so therefore the current direction will flow from B towards the ground. And I'm going to call this I sub B, because the other node is 0, so I don't have to write it, I'm just calling it here between nodes B and C, the current direction is going to be this way because VB will be greater than VC, and I'm going to call this IBC. And if I come back to node C, and the other, in this case, there would be a current flowing down from C to ground, which direction is going to be down like that. So that is I sub C flowing straight down from the node C to ground. And finally, this is a 4 M constant current, or an independent current source, which is going to push a current in this direction. So that is 4 M fixed current. I know the value. I don't have to name it. It's 4 M. So now, at the two remaining nodes, BC and BB, we have KCL. Now, at node A, there really is no inflowing and outflowing because it's the inflowing is the current coming into here and it's going to flow out. So there's really no need to write a nodal voltage at this point because it is pretty obvious, because the same current that is flowing in is going to flow out, which is IAB. So if we solve for IAB, we will exactly know what is the current flowing out of node A and what is flowing in, because they both have to be exactly the same. All right. So now we have identified and labeled all the currents. All we have to do now is to write KCL at both of the nodes B and C first, and then we will try to write them in terms of the nodal voltages. Okay. So therefore, at node B, we made the assumption, and at node B, right here, we can see that the inflow current is IAB, that is flowing into the node, and flowing out of the node is IBC, is flowing out of it, and current IB is flowing out of it. Okay, so that is the equation. And also, I can write IAB, which is the current to the 5 ohm resistor, as in relation to the voltage drop across that resistor by using Ohm's law. IAB can be written as the voltage difference across the 5 ohm resistor, which is nothing but VA minus VB divided by 5 ohms. Ohm's law, V is equal to IR, so therefore I is going to be V over R. So V over R. IBC, which is the current between nodes B and C, can be written as voltage difference between the 10 ohm resistor, the horizontal 10 ohm resistor, so VB minus VC divided by 10, plus IB, which is the current flowing from the node B to ground. The voltage difference between that will be basically VB minus 0, which is nothing but VB divided by 10, which is the vertical 10 ohm resistor. So that is the writing of the KCL in terms of the nodal voltages. Okay, so if I further simplify this, what I can do is, and I'm going to give it a name, let's call this equation number 1. Alright, now let's go to node C. So at node C, what do we have? We have a current, we will write KCL. We will write by KCL. We will get IBC flowing in. And also flowing in is the 4 amp current. And flowing out is I sub C. So IBC, we have already found. IBC is nothing but, is going to be the current that is flowing here, which is VB, the higher voltage, minus VC divided by 10. So IBC is nothing but VB minus VC divided by 10 plus 4 is equal to IC. IC is the current flowing down here. So the voltage difference between on this 20 ohm resistor is VC on one end, 0 on the other end. So VC minus 0, which is VC, which is nothing but VC divided by 20. So if I do my algebra, and I'm going to take a common denominator of 10, that will give me VB minus VC plus 40, because this is 4 divided by 1, take 200 to the other side, we become minus 200, minus minus cancel, so VB will then be equal to 20 volts. VB is equal to 20 volts. And if VB is equal to 20 volts, then all I have to find is VC. So VC, I can apply it into this equation to easily get VC. So if I substitute in this in equation number 1, then I will get 40 minus 4 VB. VB is 20. VB 20 times 4 is equal to minus 80. 80 plus VC is equal to 0. That means you will have, this implies VC is equal to 40 volts. So therefore, we have solved for all the 3 unknown voltages, VA, VB, and VC here. And once we know VA, VB, and VC, finding individual currents is just, for example, VIB would be nothing but VB, which is 20 minus 0 divided by 10, which would be 2 amps. So therefore, by doing so, we have essentially solved for the unknown nodal voltages, and by using that, we can essentially get all the currents in the Okay, this is part 3. We will be looking at using K-maps, how to do logic minimization, and we're going to use this particular example as an illustration of how to use K-maps to minimize a logical expression. So given to us is this particular problem, which is find the SOP. SOP stands for sum of products for the following expression. So a function f, inputs labeled A, B, C, and D, and the min terms are 0, 1, 3, 5, 7, 9, 11, 13, and 15. So by this point in the class, we would have looked at the definition for min terms. We would have looked at the logic minimization using Boolean expressions as Boolean expressions algebraically, and we would have looked at using those logic identities to minimize logical expressions from using minimization algebraically. Yeah. So therefore, we will be stepping on to now look at K-maps and how we can use K-maps to minimize logic expressions. All right. So given this problem, function f, which inputs A, B, C, and D, and the min terms are such, we need to solve to minimize this. So the traditional method we would have done using Boolean expressions would be that we would write each of the min terms, we would expand them out to have all the literals in there, and then we would use the Boolean identities to solve and try to find the minimum form. So here is a shortcut or a more pictorial way of doing exactly the same thing, and so these are the steps we will be following. So the first step is to look at the inputs, the number of inputs, and we are going to divide those inputs into 2 sets. Okay, the more significant ones, in this case A and B, I'm going to call them as row variables, and the least significant ones, in this case being C and D, I'm going to call them as column. Okay, so these are the names we are giving to these sort of classifications. So we call these 2 as row, and we call them as column. And here's the reason why we do that. What we're going to do is then we are going to write 16 rows. Why 16? Because we have 4 inputs and 2 raised to 4 is 16. So we would have 16 rows in the truth table. We're going to fold them into 2D, and we're going to come up with an array looking structure, which is basically 4 by 4, 16. So therefore, a K-map essentially will take the top, the more significant ones, significant inputs, and arrange them in rows. Least significant ones, and arrange them in columns. So here is how you would have arranged a 4-variable input like this. So we have an array that looks like this. So this will be a 2D array. So we need 16 locations. Okay, so I have 16 locations, 4 by 4. Now I need to assign each box to one row of the truth table. So let's see how it's done. All right, for the rows, the more significant ones will be assigned. So therefore, A and B are going to be assigned here. So A and B to the rows, C and D to the columns. So the rule in K-maps is that when we write, when we assign, because we have 4 rows, right? Each row has to have a value. So let's start with A, B both being 0 and 0. So 0, 0 means A and B are 0 and 0. So every additional or every adjacent row or every adjacent column must vary exactly by 1 bit, not more than that. So therefore, if A and B are 0, 0, then if I write 0, 1, then there's only 1 bit change, meaning B has changed. Similarly, if I go from here from the second row to the third row, I can have only 1 bit change, so therefore B has to remain at 1, however A jumps to 1. So now I have 1, 1, and then in this case, only 1 bit has to change between this row and that row, so therefore if I already have 0, 1, so therefore this has to be A remains constant and B back flips to 0. So my rows are now arranged like that. I follow a similar argument to the columns. So I start with 0, 0, and 1 bit has to change, so 0, 1. Okay, now between this column and that column, only 1 bit has to change, so this becomes 1, 1. And again, only 1 bit has to change, so this becomes 1, 0. So therefore, if you look at the, if you read it like this, A, B, C, D, if you read it in that order, see what happens. 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 1, 0, 0, 1, 0, and so on and so forth. So if I write the decimal equivalent of that inside, just for us to visualize, this box has got value 0, value 1, or row 0, row 1, row 2, row 3. Okay? 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and 15. Well, you clearly saw that this is not in order. But here is how I remember. I always think of hop, hop, skip, hop. So, hop, hop, skip, hop. Okay? Hop, hop, skip, hop. Similarly, I'm going down this row, skip, hop, hop, skip. So I start here, 8, 9, so hop, hop, skip, hop. Then I did what? Hop, 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 skip, then I go back there. 12, hop, hop, skip, hop. Alright? So if I follow that pattern, I actually have each box associated with one particular row in the truth table. Now, all I have to do is look at this minterm and say, okay, what are the minterms that are supposed to be 1, and then fill them up in the boxes. So if I do that, then 0th row is a 1. So I put a 1 over there. The first row is a 1. There's a 1. Third is a 1. So 3. 5 is a 1. So 5, 7, similarly 9, 11, 13, and 15. Okay, now that we know how to write or draw this K-map, we need some rules to sort of help us minimize and try to find the minimized form of SOP. Okay, to do that, we have some basic rules of the row. what we have to do is we have to form what's called as covers. Covers are ones, logic ones, like what we have written. We have to cover them, we have to group them in certain patterns. So we can group them in clusters of powers of 2. We will have the condition where you will have a literal and its complement being added to each other. So when we go a plus a bar, then that becomes a 1. So we don't have to, and 1 times anything is anything. We don't have to write anything times 1. So for example, here is what's going on. Let's take these two logic ones just as an example. So this position 0 means A, B, C, D are equal to A, B, C, D. They are 0, 0, 0, 0. So therefore, that's what that particular one here means. And this one here, value number 1, basically means A, B, C, D, and D is equal to 1. Because we are looking at this is 0, 0, 0, 0, 0, 0, 0, 1. Now, if you can see, when I group them together, it's very easy to see that I can take A bar, B bar, C bar outside, and I can write D bar plus D. And D bar plus D, obviously, becomes a 1. So we have A bar, B bar, C bar times 1, which is nothing but A bar, B bar, C bar. So that's why we say whenever we cover 2 ones right next to each other, we can drop the variable that changed its value. So for example, between these 2 ones right here, if I were to make a cover or a grouping like this, that's a grouping, what happens is we have 0, 0, 0, 0 combining with 0, 0, 0, 1, which is this. But pictorially, let's look at it. What changed? A and B for both ones, A and B did not change because it's the same row. Whereas between these 2 columns, C is a 0 there, C is a 0 there, so that did not change. However, D went from 0 to a 1. So since there is that flip, D changed, we will drop the D, we don't have to write the D, and then we basically write everything that has not changed, which means A did not change, B did not change, and C did not change, and they are 0, 0, 0. Therefore, 0, 0, 0, A bar times B bar times C bar is the combination that will give us a logic 1. Like this, all these ones together. Now, if I do so, between these 4 rows, nothing is constant. At least one, the A has changed from 0 to 1, B has changed from 0 to 1, 1 to 0. So both A and B have changed and they're not constant. So therefore, we don't have to write anything. A and B we don't have to write because they have changed. Now, between these 2 columns right here, C has gone from 0 to 1, which means that it's changed. And the only thing constant is that D remains unchanged at D equals 1. So therefore, this is D bar and C for the first cover, first grouping, and the second one is just D. And that is the minimized form for this particular K-map. Now, obviously, I will show them a lot more examples and work through a lot more rules and establish the rules and everything. This is just a very short preview. I'm trying to keep the video under 15 minutes and just to show an example.